freecoachingtoday.com.
So we will be learning about the Newton's law of gravitation. Newton's law of gravitation universalizes the force of attraction between any two objects that has some mass. The force of attraction between any two masses, let's say they have a mass of m1 and m2 and they are separated by a distance of d, then the force of attraction between them will depend upon the masses of these two particles in such a way that if you double this mass, the force will double. If you double the other mass, the force will double. In other words, the force is directionally proportional to the masses m1 and m2. The other rule says that if you increase the separation between these two particles, the force will become 1/4. In other words, this force is inversely proportional to the square of the distance between them. So F is directly proportional to m1 m2 divided by d square. So if you remove this constant of proportionality, we get a constant that is denoted as g. It's also called universal gravitational constant, and its value is 6.67 into 10 to the power minus 11, and its unit is Newton multiplied by meter square and divided by kg square. Newton meter square divided by kg square. So intuitively it does not look like the two masses attract each other, but it has been proven from the different observations. So what these observations are? Let's say one observation is that if we have a tree and there is a mango over it, and if somehow this mango it gets ripped from this tree, it falls towards the earth. What's happening is there is a force of attraction, and the earth attracts this mango towards itself. If you also look at that, this mango is also attracting the earth towards it. So if it starts falling towards the earth is also falling towards the mango, but because its mass is much higher compared to this mango, it's not apparent, not visible, or it's negligible. Now let's say what happens when the moon it revolves around the earth. We have a earth here and we have a moon here. Moon gets some initial horizontal velocity, something like v. Now, if there were no pull by the earth towards the moon would have continued to move along this line and would have escaped the earth's whatever attraction force or gravitational force. But what happens? The moon goes a little bit of here, it reaches here, it tries to reach here, it tries to go there. However, because of the earth's pull, its path is slightly deflected here. And the moon, instead of it were here, it comes here. Then the moon, because of it has got some horizontal velocities, tries to go here and would have escaped here, but then earth comes into picture, it again pulls the moon this way. Again it keeps, every time it tries to pull to go away from the earth's path, earth tries to pull this, and this pull is called the gravitational pull. Basically the same law, whether it's a small object falling towards the earth or a larger object moving around the circle, they are governed by the same rule. Now the reason why a smaller objects it falls towards the earth and does not move along the earth's periphery is that its mass is small and it does not have enough velocity. The closer you are to the earth, the much larger force you will need in order to rotate along the earth. We will learn about it. But if in theory, if you give it sufficiently large horizontal velocity, it can start rotating. Or if you go to certain higher height, the higher you go, the smaller horizontal velocity you need in order to make it rotate along in an orbit. So given this law, let's go through some simple examples on gravitation. We have a problem that says we have two particles. They weigh 2 kg and 4 kg each and are separated by 25 centimeters. Find the initial force of acceleration of the two particles. Let's say one particle m1, another particle m2. The other one is has a higher weight. This one is 2 kg and this one is 4.0 kg, and the separation between them is 0.25 meter. So the force of attraction is given by 6.67 10 to the power minus 11 multiplied by m1 into m2 divided by 0.25 squared. So 1 by 0.25 is 4, so we can also write it as 4 and then again 4 is 16 into 6.67 into m1 into m2. Now here's what's happening. Let's say the acceleration of m1 is a1, we denote it, so m1 starts moving and m2 also starts moving. The acceleration on m1 is given by f divided by m1, or I missed 10 to the power minus 11 here. So it's 16 into 6.67, 16 into 6.67 into 10 to the power minus 11 divided by m1, which is 2 kg. Now the acceleration of m2 is denoted by a2 is given by f divided by m2, and that will be 16 multiplied by 6.67 into 10 to the power minus 11 divided by 4 kg. Now if you look at it, m1 is heavier mass, its acceleration is smaller. a1 has less weight, so it will have a higher acceleration. That's why this vector, it denotes bigger and this vector is small. In extreme case, if this is very small and this one is very big, then this one will move at a much faster rate. It will accelerate with a big acceleration, and this one will be moving with a very small or almost negligible acceleration. This is what happens in case of Earth and a particle that falls on Earth. We will take it into another example. Click on the next video. Thank you.